till now we have seen um, concepts like stress strain, Young's modulus, elasticity, modulus of rigidity, displacement, deflection, etc. etc. All these methods have, or all the concepts have been evolved as concepts which are applied to a particular point in the material. Like for example, a stress or a strain. These quantities are at a particular point in the material or in the object. But now we will see some things which are known as energy methods. Um, Energy concepts are applied to the whole body, and they provide a direct method to calculate a lot of important parameters like deflection of beams, for example, or the rotation of beams, or the twist of a bar under a torsion. What is energy? Now, energy is defined as in when it is applied to strength of materials. It is defined as the work done by the applied load. Now, I take the example of a simple example of a bar which is fixed here, and it is pulled by a force P. Let's say the area of cross section is E, and its Young's modulus is E. Area of cross section is A, and Young's modulus is E, and the original length or the undeformed length is L. Now, in this case, if the deformation is delta L, if the deformation is delta L equal to deformation, the work done is equal to 1 upon 2 times P into delta L, because the work done that by definition means or is equal to half of the force multiplied by the displacement. So the displacement here is the displacement of the force P, which is equal to delta L. So now this, in case of strength of materials, all this work has gone into straining the bar or to deform the bar. Hence, in case of strength of materials, this work done is also known as strain energy. Strain energy. Strain energy is nothing but the amount of energy which has been stored in the bar because of the work done by the applied load. The applied load may be a moment, a torsion, or a force. Like in this case, there is a force. So let's see what happens if I convert this 1 upon 2 into P into delta L. If I convert that into material properties and stress, strain, etc. So I can write this P, I can write this delta L as P upon AE into L. Why? Because delta L is nothing but the strain multiplied by L, correct? Because the by definition strain is the ratio of the deformation to the original length, and strain is nothing but the stress upon E multiplied by L. So delta L is equal to stress upon E multiplied by L. Now stress is nothing but P upon A. So delta L will be equal to P upon AE into L. So I substitute this value here and I get this formula. So in case of a bar, the strain energy, I just say that as E, or let's say it is W, is equal to the strain energy is equal to 1 upon 2 P square L upon AE. It is normally denoted by U, not W. I'm sorry about it. It is normally denoted by U. So it is nothing but if you remember from your physics, that U used to be U was used to denote the potential energy. This is also a kind of potential energy. It is the strain potential, which means it is a potential or the amount of energy which has come inside a system because of straining. So it is denoted by U, and its value for the stretch loading is this much. Now let's solve one simple example for this to elaborate more. Um, let's say I take the example where instead of straight bar, I have this conical bar. This conical bar is having L length, same as this one, and there is a force P applied here. And let's say the width B is B here at the fixed end, which is the highest width, and it tapers down to 0 here. Let's say that the thickness is T and Young's modulus is E. Now if I want to get the strain energy for this case, how will I do that? So I have to use differential calculus now. So what I do is I take a small element. So the question is, find out strain energy of this bar. This is the bar. Find out. So how do I do this? I take a simple element here. I cut this portion here. I take a differential element like this, which has a length of dx, some length dx. Yeah. Now this dx obviously is loaded by forces which are like this, P and P, because the element is under balance of force. Now this dx, for this small portion of the bar, I know that the strain energy in this bar is, from the formula itself, it is 1 upon 2 P square into L. L is nothing but dx. L is the length of that bar, which is dx here. This is the length of the bar, upon AE. So that's the length. So I know that this is the formula for the strain energy which is stored in this bar. This is a very small bar, no big deal, sort of thing. Okay. Now here I know that P is a constant and E is a constant. So those two terms will be can be taken as a constant, and 1 upon 2 is of course a constant. But area of cross section. So what is the area of cross section here? See, it is B here, the width is B here, and it is 0 here. So obviously at a distance of x, this is the x distance, Bx is equal to width at distance x from fixity is nothing but B upon L into x. That's the value of Bx. Okay, so the area of cross section at x is equal to B upon Lx into T. T is the thickness, which is a constant. So now I take du, which is the strain energy, P square upon Axe into dx. Now I put Ax here so that to make clear that this is the area of cross section here. This is the area of cross section of this differential element. Okay. Yeah. So I just write it properly. I change the. So now I will just write the equation once more. The equation is du is equal to 1 upon 2 P square dx upon Axe. Okay. Now I want to find out what is the total strain energy which is stored in the bar. This is the strain energy. This du is the strain energy which is stored in the small differential element. So this is the strain energy for this differential element, this differential element, which is dx, and its area of cross section is ax rather. Now to get the value of u, I integrate for the whole length 1 upon 2 p square dx upon eax. I just write it in other way so that this thing can be taken as a constant. So this is nothing but, I take the constant out from the equation, 0 to L dx upon ax. Now what is the value of ax? Ax is nothing but b upon L x into t. This is what I know from the previous page. So this, again in this case, b upon L into t is a constant, so it is taken out, p square upon twice e b upon lt into t, and this equation becomes 0 to L dx by x. So this is nothing but p square L upon twice e bt, and integration of 0 to x dx upon x is log natural of x, 0 to L. So this is nothing but p square L upon twice e bt. Now what is the log natural of L? It is nothing but ln L itself. But what is the log natural of 0? That's infinite. So it shows that the amount of strain energy stored in this bar is infinite. And why is that happening? That is happening because if you see the problem here, where I am applying a force, that area of cross section is 0 there. So stress is infinite at that location. And because we are adding up the y integration, we are adding up the energy here to here to here to here to here, like that. So the energy here is infinite. Hence this problem is ill-formed actually. So if we have to solve the problem correctly, we have to take a problem in which the bar has a finite area everywhere. So we have to take a case wherein the width changes from b1 to b2. It doesn't become 0. b2 is not 0. It is a finite number, a finite positive number, which means. So for this case, it is now easy to solve. We can take, I will just take the same thing. In this case, bx will be nothing but the change of width over the length into x. That's the value of, no, sorry, this is not the value. It is b1 minus 2 by 2 into L into x. This is the value of bx, or the width at that particular location. So if we feed in this value in the equation, we get u is equal to p square upon 2e dx upon b1 minus, that's the equation. So this is now, it's easy to solve this, but we have to do one transformation, which is nothing but, we just say it is y, some quantity y. So dx is nothing but dy, or rather I'll just say minus b1 minus b2 upon L into dx is equal to dy. So I can take, now for x equal to 0, which is the lower limit of integration, y is, this is 0, b1, and for x equal to L, y is b2. Because I will put L here, so this L gets cancelled, so b1 minus b1 plus b2 is b2. So this u will become p square upon 2e b1 to b2 dx, or dx can be converted to dy upon this quantity. So that is L into dy upon minus b1 minus b2 into, this is y. So now it can, this whole thing can be taken out. It is p square L upon minus 2e b1 minus b2 into integration of dy upon y is ln y b1 to b2. So that is nothing but minus p square L upon twice e b1 minus b2 Now, this will be ln b2 minus ln b1, which is ln b2 by b1. Now, obviously b2 is smaller than b1, so this quantity will be negative, and there is a negative sign outside. So I can always invert the thing. So it becomes p square l upon twice e b1 minus b2 into ln b1 upon b2. That's the answer for this problem. Now, obviously, in this case itself, in this case, we can see what happens if I put b1 is equal to b1 is equal to b2. Now, in this case, if I put b1 equal to b2, I will get indeterminate answer, because b1 is equal to b2 means this is 0 and both numerator and denominator will become 0. So this equation cannot be used to get the value of simple square beam, because simple prismatic beam, because for that case the equation has to get solved before integration itself. If you do integration and then solve, there will be a log. So I gave the example to bring in the point that if you do not have a uniform force or uniform stress throughout the material, then this is the way you have to solve for it. Now let's see what is the strain energy for torsion and for bending. So the strain energy for torsion, similarly as this one, is the strain energy for torsion is given by 1 upon 2 T square L upon G into J. It's exactly the same formula as what we have for the direct loading. The only thing is that the load instead of P is T and everything else is just analogous. So this is the strain energy for torsion. Similarly, now if we have a simple problem, now let's solve one problem, which is I have a bar, actually it's a tube, let's say that's a tube. Now this tube is made of it is a thin tube, and it's let's say its outer diameter or outer radius is RO, that's outer one, and the inner radius is RI. So, and the material constant is G and the torque applied is T. Let's say the length is L. So in this case we have to find out the strain energy. So the strain energy in torsion will be equal to 1 upon 2 T square L upon G into J. Now J is nothing but pi by 2 into RO to power 4 minus RI to power 4. So if I just if I just simplify this formula, it will become T square L upon pi G 4 minus RI to power 4. Now let's see another problem. The same problem, if I have a bar instead of a tube, now I have a bar which is made of some radius R, and other things are all same, it is having G and length is L. So in this case the strain energy, now there is another T, torque T here, strain energy will be equal to 1 upon 2, let's say this torsion is T dash, so T dash into T dash square rather L upon G into its J, which is pi by 2 into R square, R to power 4. Now if somebody asks the question that if this torsion and this torsion are equal, if it is given that the torsions are equal, then if I can ask the question, what is the value of R for which the energies will be equal? So in that case I have T square L upon pi G RO to power 4 minus RI to power 4, that is equal to, the torsion on the other side is also equal, T square upon T square L upon pi G R to power 4. So that shows that R to power 4 is RO to power 4 minus RI to power 4. Now that equation cannot by itself solve the value of, what is the value of R. For that you have to fix both the values. But if you have fixed the values, then it is easy to see that R is nothing but 4th root of Ro to power 4 minus Ri to power 4. So if this is the value of the radius of the bar, then it will have the same energy as the value of as the tube will save. Obviously, it's not easy to guess that the tube will probably deform, probably rotate or twist more in case its outer radius is almost equal to the radius of the bar. So that's about torsion. Now let's see what is the strain energy for bending. Now that's another interesting case. Strain energy for bending. Strain energy for bending, it is given by this formula. Because in most cases the bending moment is not constant over the whole length. If it is constant over the length, then this integration can be done very easily by doing this. This is the formula for pure moment if m equal to constant, which normally is not the case. Hence, this is the formula which is applied for strain energy. Now, strain energy seems, I mean, this formula seems to be like, I mean, this is the only integral formula. It occurs in a form of integral. Now, let's see a problem which is heavily useful. I mean, this problem will probably be very useful for you in exams. Let's see this formula, this problem, which is the strain energy for cantilever beams. Now I have a cantilever beam which is having an end load of P, and this is the length L. Now at any section here which is at a distance of x, I know that the value of m is the bending moment there is equal to P into L minus x, correct? Because that's the value of bending moment there. I can of course take the variation of x from this side also, but it doesn't matter, in values will be same. So now I use this number 0 to L, P L minus x squared out upon 2 EI into dx. Dx is the small length here of the beam. This is the value of the strain energy stored in this cantilever beam. So I just do the integration. This is nothing but p square upon twice EI. It comes out L minus x whole square dx. Now I can do the integration directly by expanding this equation in 0 to L. So it becomes L square dx plus x square dx minus 2lx dx. So now it is p square upon twice EI. I can do the integration here, this L square, that will be 0 to L plus x square by 3, x cube by 3, sorry, 0 to L minus 2L x square by 2, 0 to L. So that becomes p square upon twice EI. This is L square x, sorry. It becomes L cube, 0 is 0 plus L cube by 3 minus this gets cancelled out, so it becomes L cube again, right? This is x square, is when L is substituted, it becomes L square into L is L cube. So this gets cancelled out. So the value of strain energy is P square L cube upon 6 EI. That's the strain energy which is stored in the cantilever beam. Now twist. What is the value of deformation of the strain of the cantilever beam? We know that the deformation is I mean, let's say delta is the deformation, it is PL cube upon 3 EI. We know it. How do we obtain this now from this cantilever beam example? So what we do is that we know that the energy stored is nothing but this. So that is equal to P square L cube upon 6 EI. So from this we can get delta is equal to P L cube. This gets cancelled out, 3 EI. So without solving the complicated equation of integrating twice, I mean you use the curvature, integrate that twice and get the deformation, you can directly get it from here. So that's why this example is very, very important to bring in this point, that you can solve for any problem using strain energy. Let's take another example, very simple example again, but it brings in the point. We have, this is simply supported beam. It has load P at the center. Now, what is the bending moment at any location here? This is x. That bending moment at x is equal to P upon 2 into x, because the force will be P upon 2 here and the force is P upon 2. So the shear force is P upon 2 everywhere, and a distance at x is at a distance x, the moment will be P upon 2 into x. So the strain energy is nothing but integration of 0 to, now we have to integrate it L by 2, because this moment is varied only from 0 to L by 2, and multiplied by 2 for the other half, this half, this half, this half I can cut it here. So for that half, this is the formula. Similarly for that half, same thing is the formula. So this I do, and this value will be nothing but P by 2x square into dx upon EI. So I can take this out. M square upon twice EI. So this 2 gets cancelled out by this. So this becomes 0 to L by 2 P square by 4 EI x square dx. Correct. So now I can integrate this very easily. So it becomes P square upon 4 EI x cube by 3 and 0 to L by 2. So that is P square upon 4 EI. This becomes L cube by 24. Now I know that the deformation will be, let's say the deformation is delta. So U is 1 upon 2 P into delta, correct, because the force is P. So 1 upon 2 P into delta is nothing but P square L cube upon 96 EI. 24 by 4 is 96. So I know now delta is equal to P square P L cube upon 48 EI. That is actually the answer. So using this method, you can very easily get the deflections for beams, or the rotations for twist for torsion, or the stretch for direct loading and all that. So please do a lot of problems in this. This is a very important concept, and this is very important concept because it doesn't need much integration etc to be done. You can directly do the solution using energy and get the value of deflections. So that's a very good concept and very important, and it is very heavily used in higher concepts like finite element analysis and all.